Okay, I think we'll get started. So today we're going to walk through the datasheet, just some of the features. I encourage you to download the PDF of the datasheet. It's readily available online, and it's worthwhile to read through it and to highlight all the things that you think are important with regard to the PIC10F200. We're going to do some of that today, so familiarizing ourselves with some of the aspects of the PIC10F200, particularly those that we'll run into as we work through the labs in this series. All right, so let's go to the DocCam and look at some of these features. All right, so we're going to just step through the data sheet as best we can here, and I'll just try to highlight some of the features of the PIC10F200. The 10F200 is the simplest of all of the PICs. It's got the least amount of memory, least number of input-output ports. It's in the baseline set, so it has the fewest number of instructions, along with a whole bunch of other PICs that are in that same baseline family. But it's a good one to start on in that you can get your mind wrapped around it. You can easily think about all of the different file registers, memory registers, and so that's the motivation for this series. And so let's go ahead and start looking through this. So the datasheet, as is often the case, will involve many or several PICs at the same time. So of course we're working with the PIC10F200. So let's just look at some of the features, and these have a lot of common features, although what we'll see is that there are some aspects such as a comparator that the PIC10F200 does not have. All right, so in terms of learning to code in assembly, so we'll be talking about assembly code, it's a small instruction set, so only 33 single word instructions, and so you can have, and they're all listed in here, a table with a little cheat sheet which we'll get to, and then actual elaboration of the instruction set. So pretty easy to follow and to learn. The instructions are single cycle except for the branch, and so the chip runs at 4 megahertz clock, and the instruction cycles are then 4 clock cycles, so 1 megahertz instruction cycle. And then as this is stating, each instruction except for the branch, like calling a function, for example, or go to, these will just take a single cycle. The stack is too deep, so we can call a function and then call a function within that function, but we can't go any further than that. 4 input-output pins, well actually 4 potential input pins, 3 output pins. So 3 are bidirectional, so we can control, based on how we set up the PIC, just if we want it to be an input or an output. And then 1 pin, pin 3, is actually just an input only pin. And so this is a summary here of the features. 4 input-output, no comparators. So we see for the 204 and the 206, we would have 1 comparator pin as well, which of course would be handy, but here we're just learning how to do this, so keeping it simple is the idea here. All right, so we're going to be working throughout with DIP type configuration, so these will be good for working on the breadboard. And so the typical one for a 200 is this one here, and we'll start to get used to this. There's a couple of pins that it's really only a 6-pin device, but this is in an 8-pin package. So pin 1 and pin 6 are not used at all. and they don't need to be grounded. They can just float. They're just not used. Then the ground is the second pin down on the right side, so pin 7, and the 5-volt rail, and this is a 5-volt, it's driven by 5 volts, is on pin number 2. The outputs GP2, GP1, GP0, and GP3. So these are input outputs here, and this is input only. GP2 is also used for an external clock. We won't be doing anything with an external clock, but we will have to know that because we'll need to turn that off and turn it on such that this is viewed as an input-output pin. The remaining values here refer to programming the PIC, and so when we use our PIC-Kit 5 to program this, we'll need to wire these appropriately, and we have got a video on that. Just kind of recapping here, 4 megahertz clock cycle, so a 1 megahertz instruction cycle, total memory of 16 memory units, 8 of which we can have full freely for us to use, and the others are dedicated, but we can read and write to them. 3 input-output pins, or 3 input-output pins and 1 output-only pin. Now let's look a little bit more closely at these pins. So pin 0, GP0, that's the name of that pin. So when we're writing code, we will just refer to GP0, and that's a single bit, and it'll be either on or off. And if it's an output pin, then we can read whether that's on or off, a 1 or a 0, so 5 volts or 0 volts. If it's an input pin, then if we're applying 5 volts, then it's a 1 or an on, and if we're applying ground, then it's a 0 or an off. Same is true for these. The GP2 is also the clock pin, and it actually defaults to the clock. So we'll talk about that in a little bit. And then GP3 is an input-only pin. So we can't drive an output with that, but we can use it as an input. Here's, I won't say too much about this, but a bit on pipelining. So 4 clock cycles constitute a single instruction cycle. And then in terms of the pipelining, we get then 4 pipeline events happening in sequence here with these clock cycles. We talked about, I mentioned that there's some memory registers that's free for us to use, and then there's some special registers, and here is most of them. So these have the index 0x and in hexadecimal, and only goes up to, well, there's 8 of them, so 0 through 7. And these are indef, which we'll talk about. This is for indirect addressing, so we can use pointers here. And this in combination with the file select register, so these two together give a strategy for indirect memory access. And this is useful when you're trying to write things sequentially to the different memory registers, and so you can put that in a loop, and that is very handy in that regard. We won't talk too much about most of these. Status is something that will flag various things, such as is a result of an operation a 0? Does it need to carry a bit? We won't talk really a lot about that, so we won't say too much about that. We won't say much about the OSCAL or the PCL. GPIO, So these are the last 4 bits, and this refers to the input-output pins that will be looking at. Tris, it's called Tris GPIO here, but that's it's referred to in the coding as Tris. This is what we use to set whether these pins are going to be output or input. So these here are what the values are, and then here is this controls whether we are using them as an input or output. And a 1 is an input, and a 0 is an output. So let's say we wanted pin GP0 to be an output and the others to be input. What we would do is we would write a binary, and the first 4 don't matter, so they could be anything. And then we would go 1, 1, 1, 0. Right? So in general, this is a binary 0, 0, 0, 0, 1. Sorry, 0, 0, X. Well, 1, 1. Yep, because this is GP3, which is always 1. And then this is X, 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 where X is equals 0 or 1. And so for the example we were talking about here, this would say GP0 is an output, and GP3, GP2, and GP1 are all inputs. And so that's how we'll end up controlling that. And the last one is the option register. We won't say too much about that, but this bit here controls whether we're using an external clock and we want to use the pin GP2 as an external clock, or as an input-output. It defaults to the external clock, so we'll need to write that. And actually, yeah, I'll talk about that right here. So I think I'm pretty sure it defaults to all 1s across here. And so what we're going to need to do is write again a binary, and we're going to go 1, 1, 0, 1, 1, 1, 1, 1. I think that's, yep. And it's this pin here. We want to turn that, or that bit there, we want to turn that to a 0. And what this does is it makes GP2 an output, input-output. If it's a 1, then this is a clock, external clock. And don't worry too much if this is already not understanding this so well. Just go through this, try to get what you can out of this, start doing the activities, and then come back and watch this video again. Sit down with the data sheet, and I think it'll become clear. I have really enjoyed learning about this, and it does seem overwhelming at first, but then it comes along pretty well. All right, not going to say too much about this right now, but this indef and the special the file select register are used in tandem to do some indirect addressing. So we are going to we'll have a lab on this where we explicitly do both reading and writing via indirect addressing. But essentially what happens is indef is not a physical register, and it's actually using what's in the file select register as a pointer to the different physical memory registers. And I guess I should say here, the physical memory registers are 0x, 1x, well, let me call this, yeah, so 0x10 through 0x, so this 0x1, this means hexadecimal, through 07. So we have 8 registers to use, 8-bit registers. So we can store an 8-bit piece of data, whether it's an ASCII code or a number, in these registers. And it's 8 isn't very much, but it often gives you enough to do some fairly elaborate code. And we will have a number of examples and builds that involve utilizing these different memory, whether we are doing indirect addressing or direct addressing. So you can write directly to those as well, and the individual those 33 instructions, which we'll get to in a bit, give us the ability to change a single byte on a given bit, and so we have complete control over the memory on this chip. Right. I think I've said probably enough about the I/O ports. So again, GP0, GP1, GP2, GP3, these are the names they'll be referred to as. And so we'll write things like bit set F GP0. So that would be setting GP0 to on, for example. So we're referring to this. This is the name that we use. Now, notice here, this is the order of precedence. So this is after the programming here. So when it's just acting naturally, 0, 1, and 3 are always in their input-output modes, but we're actually in the clock mode for GP2. So again, as I mentioned earlier, that's why we have to switch that in the option register, such that GP2 is an input-output. Let's see. Not too much here. Again, it's TRIS, not TRIS GPIO. So in some of the older code you might find on YouTube, it will say TRIS GPIS or GPIO, and for a while it was hard for me to figure out why this wasn't working. But yeah, you have to use TRIS. There is no TRIS GPIO command. And so this is the name of, this is the name of the register, but its name when you're calling it or writing to it is just TRIS. And again, it's these last 4 bits that matter, and that's what turns into input or output. Okay, so now let's look at the instruction set. So again, just 33 words. They're broken down into 3 categories. Byte oriented, so this is working on a whole byte. So that might be moving a register or something like moving something to the working register or whatever. Then a bit, so this might be reading a GPIO port, or it might be setting a particular bit in a memory. And then literal and control. So these, one thing we'll use a lot is to just put a number, and like a decimal number or a base 10 number, into the working register, and then that will be used in a variety of ways. That base 10 number, or it could be binary, it could be hex, that number is called a literal. Okay, so here, this is the whole set. So there's a nice little summary sheet here, and so I don't want to say too much, because we'll be going through a lot of examples and you'll be looking at the code. But I just want to identify some of the structure here. So let's just look at this first command. This is going to add the working register to the file register, and this is something that easy to get a little confused on. So let's say we want to add the working register, right? So whatever we have in the working register, we want to add that to, say, register 0x10, right? So then we would write add, and you can go capital or lowercase, doesn't matter. I tend to write mine in lowercase, but you certainly could write them in capital letters. and then we would put the file, so F stands for file, so that's going to be 0x10, and then comma, D stands for the destination, and if it's 0, so we could go 0 here or 1. If it's 0, it will put the result in the working register. If it's 1, it'll put the result in the file register. So it will modify it will actually modify what's in here and write then the addition. If you don't want that, you want it to go into the working register, then you would put 0. And that's common for a lot of these things. Notice there isn't one here. This is moving the working register to a file register. So that's a common thing to do as well. So you've done something with the working register, and now you want to put it in file. And I should say that there's always, the working register always plays the intermediary. So let's say you wanted to add 10 plus position 11, or 1 0 and 1 1. You can't just add these directly. There's no function that will add these directly. What you have to do is stick 1 into the working register, then add, and then put the result out. So the working register is always playing the middleman in all these transactions. All right, let's look at some of the bit here. Let's say we want to clear, this will clear a bit, so we'd say bit clear F 0x10, and then we can go 0 through 7. So there's 8 bits, but they start with 0. So let's say we want to clear the third bit, so change the third bit to a 0. So then we would just put 3 down here, and so that would be, so let's say it was originally 1 1 1 1 1 1 1. Then third bit is here, I think. So this would be 1 1 1 1 1 0 1 1. Let's see, sorry, 0 1 2 3. So third bit would be here. Yeah, I was a little confusing there. So we could put 0. That would be this one. 3 means the fourth bit over. So 0 1 2 3, and so that would be this one here. And then finally, literals. K is used to represent a literal here. This is a very common thing we'll do. Move a literal to the working register. Just want to show you here, I've just copied the first page of the whole, the nice thing about the data sheet, it has all of these instructions, and then it's written out this way. So the first one here, add, and it then gives you a bit of an example, and it helps you remind you, okay, this is the file. So what we'll do here, although this is a yes, 0 to 31, but we're going to be putting things in like this. And then destination, notice this is either a 0 or a 1. Again, 0 brings us, puts the result in the working register, and 1 puts the result in whatever file that you're using. And then here's example, clearing a bit. So again, the file again will be something like that, and the bit, now B, that can be a number 0 through 7, and this helps remind you of that. I just want to point out one more that is very important, and that is there's a skip if clear and a skip if set. And this is really what gives the power to the assembly code, is having these instructions, because this allows you then to test things, and we'll use this a lot to see if an input is on or off, or if a particular part of a file is on or off. And maybe in line with this, I'll also identify this function here, decrement the file. So every time it runs into this, it'll drop the value, the binary value, so like the actual value of the file, by 1, and then skip if 0. So this is a great way to really institute essentially a for loop. You have some value in your memory, and then it counts down, and when it hits 0, then so it counts down, and if it hits 0, it will skip the next line, and what you have is in that line that you're skipping is the go-to that sends you back in that loop, and so you want to skip out of that. And for the PIC10F200, it's 8-bit, so we can count loops as big as 255. So you can set it to 255. It'll count down to 0. So I guess 256 iterations is the largest loop. And then you can nest loops, and we'll talk about that as well. Okay. All right. So I think that's it for this quick survey through the data sheet. And again, I encourage you to actually sit down and read it. It's it's kind of dry reading, but it's actually pretty good, and I think you'll learn a lot from that. And typically, when you look at, if you were to buy a book, there are some books on PIC. The books are really just an elaboration of the data sheet. It certainly can be very good and valuable, and you should consider those as well. But don't be intimidated by looking at the data sheet. It has some really valuable information. It can really help you learn quickly. And again, as I said about halfway through, this is all complicated at first, and as you just work with it and fail and try again and fail, that's what's nice about electronics, and computing. The response time for a failure is usually very fast, and so you can fail and try again, fail and try again many times in a 10-15 minute period. And that's how you learn, and so hopefully you'll enjoy this series and learn a lot about PIC microcontrollers, and that will have some transferable skills, certainly to the more elaborate PICs, but also or the higher level family of PICs, but also to the other common microcontrollers. And then the good thing about this is all focused on assembly language, so of course ultimately you'd probably be coding in C, and then even in some, like the Raspberry Pi and the Raspberry Pico, you can code in Python. By knowing what's going on down at the register memory level, it just makes you stronger in your understanding when you utilize that higher level code, higher level programming language to control these microcontrollers. All right, so I think that's it for this video, and so onward to the different labs and activities.